These are the notes for AP Calculus on the topic of analyzing the graph of the first derivative. So it says the figure below shows the graph of f prime, the derivative of the function f, on the closed interval from -8 to 7. The graph of f prime has horizontal tangents at x equals -3 and x equals 4. So they're telling you that just so you can tell exactly where it is, so you don't have to guess where those horizontal tangents are. And it says the function f is twice differentiable. You can take the derivative of it twice with f of 0 equal to 5. So the first thing they're asking us for part A is to find the x-coordinate of each local minimum of the graph of f and then justify your answer. So remember, when you're finding local minimums or local maximums, you use the first derivative. So we've got the graph of the first derivative right here. So then what you can do is just draw yourself a number line right underneath this graph. Okay. And this number line represents the first derivative. So we can label it f prime of x. And the first thing we look for is, remember when you're looking for local mins or maxes, is where the first derivative is 0 or undefined. So let's see where the first derivative is 0 here. And you can see right here at -7, the first derivative is equal to 0. So we'll put that down on our number line. That's one of our critical numbers. Also right here at 0, the first derivative equals 0. So there's another critical number. At 0, the first derivative is 0. And over here at 6, the first derivative is 0. Okay, so those are our three critical numbers. And then what we do to test in between here, instead of plugging them into an equation, like we have done before when we have the equation of the first derivative, what we do is look at the graph. And what we look at since this is the graph of the first derivative already, we're just looking, just like we looked at here, these were the y values are equal to 0 at these 3 points. We're looking at the y values to see if they are positive or negative. Because this is the graph of the first derivative, so we're just looking at its values. So we can see from -8 to -7, these y values are all negative, below the x-axis. From -7 to 0, these y values here are all positive, above the x-axis. From 0 to 6, these y values are all negative, below the x-axis. And from 6 to 7, you can see that y values here are all positive above the x-axis. So remember what this tells us, this is called the first derivative test. What this tells us about the original function, f of x, it's the slope of the original function. So if the slope of the original function is negative, the first derivative is negative, the original function f of x we know would be decreasing. If the original function has a first derivative that's positive, the slope is positive, then we know the original function is increasing. Then the first derivative is negative again, so the original function is back to decreasing, and positive again, back to increasing. And now we can look at our critical numbers and see if they're actually relative minimums or relative maximums. So at 0, first derivative changes from negative to positive, so that's a relative minimum. So it goes from decreasing to increasing. At 0, the first derivative changes from positive to negative, so that's a relative maximum. And at 6, the first derivative changes, again, from negative to positive, so that's another relative minimum. So now if we go back to part A, we were asked for what are the relative minimums. The x values, they're -7 and 6. So for part A, we can say f has, in this case they're called local minimums, but the same thing as relative. So local minimums at, it's only asking for the x-coordinates, so at x equals, look back here, it was -7 and +6. So it's -7 and x equals 6. And then justify your answer. Okay, so we justify these in the same way when we had the equation of the first derivative. Since you have to refer to the first derivative, since f prime of x changes from negative to positive at, and you have to specify where it changes from negative to positive, at x equals negative 7 and x equals 6. So that would be your answer with your justification. Then on part B, it says find the x-coordinate of each of the points of inflection of the graph of f and justify your answer. So points of inflection, recall, those come from the second derivative. So let's go back to our graph here. We've got the graph of the first derivative, so now let's draw another number line underneath this one. Except this one's going to represent the second derivative. So we'll label this f double prime of x. But now when we're looking at the second derivative, we don't have the graph of the second derivative. We have the graph of the first derivative. So you just have to remember, well, how does the second derivative relate to the graph of the first derivative? Well, the second derivative represents the slope of the first derivative. So that's what we're going to have to look at here, is the slope of the first derivative. That'll give us what the second derivative is. So right here, if you think about the tangent line here, the slope is positive until we get to our horizontal tangent line. It said was at negative 3 right there. So right there, the slope is 0. So that'll be key point, one of our possible points of inflection. Negative 3, the slope is 0. So it's positive all the way until x equals negative 3. And then you can see the slope is negative all the way until we get to the other horizontal tangent line, which it told us was at 4. So it's negative all the way until 4. And notice how I'm lining up the number lines as best I can right underneath the graph. That'll make it a lot easier to get things accurately, especially when we get to the graphing part of this. So at 4, 0, and then after 4, it's positive the rest of the way. So remember what the second derivative tells us about the original function, f of x. It shows us when the second derivative is positive, the original function f of x is concave up. And when the second derivative is negative, the original function is concave down. And then back to positive, concave up. So now we can see, well, we're looking for points of inflection. Is negative 3 was a possible point of inflection because the second derivative is 0 there. And since it switches sign and switches concavity, it is actually a point of inflection. So negative 3, just abbreviate that here. It's a point of inflection. And 4, it also switches concavity. The second derivative changes sign. So that's another point of inflection. So now we can answer part B and say f has points of inflection at, let's look back at our graph real quick, x equals negative 3 and x equals 4. And again, it says to justify your answer. So just like we did before, the reason why we know these are points of inflection, it's since f double prime of x changes. Here, unlike local mins and local maxes, it doesn't matter which way it changes, from negative to positive or positive to negative. So you can just say changes sign. Again, refer specifically to it changes sign at x equals negative 3 and x equals 4. And then part C says find all the intervals on which the graph of f is concave up. So if the graph of f is concave up, well, that would mean that the second derivative, f double prime of x, would have to be greater than 0 or positive, and has a negative slope Well, that would refer to the first derivative. First derivative is the slope of the graph. Would have to be less than 0, or negative. So let's go back to our number lines here and look for where the first derivative is negative, but the second derivative is positive. That says find all the intervals on which that's true. So first derivative negative, second derivative positive, that's our first interval. Except notice it doesn't go to negative infinity. We've just got the closed interval from negative 8 to 7. So we don't know what's happening past negative 8 to the left of that. So it actually would start at negative 8, and you can see that stops at 7, where the first derivative is negative and the second derivative is positive. Because after negative 7, the first derivative changes to be positive. So negative 8 to negative 7 would be our first interval. So we can say f is concave up with a negative slope. Now notice when you're talking about points, like points of inflection or local minimums, you say at. When you're talking about intervals, you say on. So on negative 8 to negative 7. Let's see if there's anywhere else. Okay, the first derivative negative, not here. First derivative negative here. First derivative negative, second derivative positive, so also between 4 and 6. So and 4 to 6. And then you explain your reasoning. Another way of saying, like, justify your answer is, again, since f double prime of x is greater than 0, that makes it concave up, and f prime of x is less than 0. And you could say these intervals again, or you could just say on these intervals. Now let's take a look at how we can actually sketch a possible graph of f on the axis provided below. Again, from just negative 8 to 7. So if we go back to our first derivative, there is one point we know on the original function, and that's right here. It says f of 0 is 5. So what that's giving us, as we know for sure, the point 0, 5 is on the graph of the original function. So let's start with that. 5, put that right there. But that's the only point we know for sure. The rest of it we have to base simply upon our number lines here, where the function is increasing or decreasing and where the function is concave up or concave down. So it's easiest to go left to right to make sure you get the increasing and decreasing right. Let's start with where our first point is. It's at 0, 5. So from 0, and then whenever you look at both number lines at the same time, whenever either number line changes sign, that's where you want to stop. So from 0 to 4, we know the function needs to be decreasing, concave down, shaped like a frown. So from 0 to 4, now we don't necessarily know which the y value is going to end up at, so don't worry about that, because we don't know for sure that. We just have to make sure it's decreasing, concave down, shaped like a frown. So decreasing, concave down until we get to 4. So again, don't worry about if your y value is exactly where mine is at. Okay? And then from 4, go back to our number line. The next time something changes is at 6. The function is still decreasing, but now it switches to concave up, shaped like a cup. And notice right at 6, the slope is 0, so it levels off at 6. So from 4 to 6, decreasing, still concave up, shaped like a cup. Again, we don't know what the specific y value is, but we know it's decreasing, concave up until we get to 6. So level it off there. I'm just putting these points a little bigger here so you can see that's where something changes. Okay. And then from 6 to 7, we know the function's increasing in concave up, shaped like a cup. So from 6 to 7. And just stop the graph at 7 because we don't know what's happening after that. So that's as far as we know the first derivative. Now, going the other direction is a little bit trickier. But again, we use the fact that we know it has to go through 0 to 5. So we go back to our number lines here. The next interval I would look at is right up until that point. From negative 3 to 0, the function is increasing and concave down, shaped like a frown. So it's got to level off at 0. So increasing concave down from -3 to 0. And it's got to increase to get to this point, so it's got to start below it. So increasing concave down. And let's look at the next interval now. From -7 to -3, it's still increasing, but now concave up, shaped like a cup, until we get to -3. Okay, so increasing from, let's see, that was -7 to -3, concave up. So again, to increase, it has to start below that, so increasing concave up. We don't necessarily know where it is. So don't worry about the exact y values. Increasing concave up. Let's try that again here. Doesn't have to be perfect, just do your best to make it a nice smooth curve there. And it levels off there at -7. So increasing concave up. You can see it levels off at -7 because the first derivative is 0 there. And then from -8 to -7, we know the function is decreasing concave up, shaped like a cup. So decreasing concave up. To decrease to get to that point, we know it has to start above it. So decreasing concave up, shaped like a cup. Yeah. So again, don't worry about these specific y values. The only one we know for sure on this one is that red point right there, because that's the point we're given. The rest of it, the y values may be slightly different, but your overall shape of the graph should be the same. It should have the correct increasing, decreasing intervals and the correct concavity. And that's why it says a possible graph. Okay? But there will be a little variation in where you put your y values. Okay, let's take a look at another example now. This one says, let g be a function defined on the closed interval from -8 to 9, with g of 2 equal to -1. And the graph of g prime, the derivative of g, consists of 2 semicircles and 4 line segments, as shown below. Okay. So the first thing we're asked here in part A, find from -8 to 9, find all the values of x which g has a relative maximum. Again, relative mins and maxes come from the first derivative. So in this case it's g. So let's draw a number line. For g prime, the first derivative. So g prime of x. And again, what we're going to be looking at, since this is the graph of the first derivative, we're looking at the y values. Whenever the graph is the same as your number line, you're just looking at its y values. So you can see the y values start off being positive here, from -8 to -6 there, until we get right there to -6. See, the y value is 0. But then after -6, they continue being positive y values all the way until 0. The y value is 0. But then after 0, now the y values are negative until we get to 5, or the y value is 0 again. And then from 5 all the way to 9, it's back to positive. And then right there at 9, it's 0 again. So again, what this shows us about the original function, this is the slope of the original function. This first derivative is positive. The original function g of x must be increasing, and then still increasing, decreasing, and then back to increasing. So -6 was a critical number because the first derivative is 0 there, but it doesn't switch sign, so now that's not a relative min or a relative max. At 0, the first derivative changes from positive to negative. It goes from increasing to decreasing, so that's a relative max. And at 5, the first derivative changes from negative to positive, so it's going from decreasing to increasing, so that's a relative minimum. So we're just out of relative maximums here, which occurs at 0. So now we can write g has a relative maximum at x equals 0. And again, this is a justifier answer, so your justification would be since g prime of x changes from positive to negative at, you can specify at x equals 0. And then part B asks for when x is between -8 and 9, find all the values of x at which g has an inflection point, and justify your answer. So remember, inflection points come from the second derivative. So let's go back to our graph here. And draw another number line right underneath this for the second derivative, g double prime. So g double prime of x, the second derivative. And again, when you have the graph of the first derivative, remember the second derivative is the slope of the first derivative. So that's what we're going to be looking at, is the slope. So we can see the slope starts out being negative until we get to -4. And at -4, we've got a corner there. So there the slope, you could either say is undefined or does not exist. And then from -4 on, the slope is positive. Notice it tells you it's a semicircle, so right in the middle there, right there at, sorry, that was not -4, that was -6, my bad. That was -6. And then so from -6 to -3, you can see the slope is positive. And then right at -3, the slope is 0. It levels off right there. And then from -3 to 0, the slope is negative again. Right there at 0, you see we have another corner. So at 0 again, we'd say the slope does not exist. And then the slope is negative until we get to 2. We got another corner there, an abrupt change in the slope. So again, it doesn't exist right there. And then from 2 to 4, notice the slope is just 0 the whole way. Until we get to 4, where we've got another corner. So again, the derivative, the second derivative here, or the slope doesn't exist. Then it's positive until 5. Another corner, so it does not exist there. From 5 to 7, it's positive slope. And right at 7, it levels off, so there's a slope of 0. And then finally, from 7 to 9, the slope is negative. So we've got a whole bunch of possible points of inflection here, where the derivative is 0 or doesn't exist. So what this shows us about the original function, g of x, is the second derivative is negative. We know the original function is concave down. Second derivative positive, it's concave up. Negative, concave down, still negative, concave down, 0. Well, if it's not positive or negative, if it's 0, the only other option if it's not concave up or concave down is if the slope is staying the same. In this case, that would mean it's 0, so that means it's linear. So the linear function, a straight line, is not concave up or concave down. And then from 4 to 5, it's positive, so back to concave up. 5 to 7, still concave up. And then 7 to 9, now it's back to concave down. So let's see where we actually have inflection points, where the second derivative changes sign here. So at -6, it changes sign. We have a point of inflection there. At -3, it also changes sign, the second derivative. 0, it doesn't change sign. 2, it doesn't change sign because it goes from negative to 0. And neither at 4 goes from 0 to positive, so it has to be a point of inflection. 5, it doesn't change sign, but 7 it does. It changes from positive to negative, so there's another point of inflection. So out of our possible points of inflection, only 3 of them, -6, -3, and 7, actually turned out to be points of inflection. So -6, -3, and 7. So you can say g has, in this case they're called inflection points, same thing. Inflection points at, again it just asks for the values of x, so x equals -6, x equals -3, and x equals 7. And again, to justify your answer, you would just say since g double prime of x changes sign at x equals -6, x equals -3, and x equals 7. Then for part C, it says find all intervals on which the graph of g is increasing and concave down. So if g is increasing, that means the first derivative, g prime of x, would have to be positive or greater than 0. And if g is concave down, that would mean the second derivative of g double prime of x, would have to be negative or less than 0. So now we're looking for the first derivative is positive and the second derivative is negative. Okay. So let's look back at our number line here. Both number lines, I should say. So we want it to be increasing concave down, first derivative positive, second derivative negative. So we can see it starts off that way, from -8 to -6. So we can say g is increasing and concave down on -8 to -6. Let's see if there's anywhere else where the first derivative is positive and the second derivative is negative. So it's also from so first derivative positive, second derivative negative, also from -3 to 0. From -3 to 0. And I think I saw one more place if we go back there. First derivative positive, second derivative negative, also from 7 to 9. And again, the justification, or in this case it says explain your reasoning, same thing, would be since g prime of x is greater than 0, that's what makes it increasing, and g double prime of x is less than 0, so it makes it concave down. And finally, in part B, says from -8 to 9, sketch a possible graph of f on the axes provided below. So let's look and see if we have any points we know for sure. And it tells us right here, g of 2 equals -1. So that means we know the point 2, -1 is on the graph. So 2, -1 right there. That's the only point we know for certain on the graph, for now. But now let's take a look. Let's start from 2 and go to the right from there. Then we'll work our way back. So back to the number line here. Starting from 2. Oops, I forgot to write on the number line here. From 2 to 4, that's where it was linear. It was decreasing and linear. So that's where it's a straight line. And to see exactly what the slope is, well, we have the graph of the first derivative, which is the slope, right? So if you look at the y value right there between 2 and 4, we can see it's -2. So that means we know the slope of the graph from 2 to 4 is exactly -2. It never changes. It stays a constant -2, which is why it has no concavity to it. So if we just go down to right 1, that'll give us what the graph looks like. So from here, if we go down to right 1, there, and again down to right 1, right there. So this one we know is a straight line. It's linear. So we do have some other points we know for certain right there. because it's linear. Now let's look from 4 on what it looks like. Let's go back to our number line here. So from 4 to 5, for that little section, it's decreasing, concave up. And it levels off, looks like at 5. So decreasing, concave up, shaped like a cup. And we want it to be a smooth transition there at 4, I think, because the first derivative just stays negative the whole way. So decreasing, concave up until we get to 5. Oops. Try to make that a little smoother there. So levels off at 5. Again, don't worry about the exact y value there. And then let's look what happens after 5. From 5 to 7, now it's increasing, concave up, shaped like a cup. From 5 to 7. And don't worry about the exact y value. And then from 7 to 9, it still increases, but now it switches to concave down, shaped like a front. Still increasing, concave down, shaped like, and it should level off right there because the first derivative was 0 right there. Okay. Now let's work our way back to this point. So let's see what happens until we get to 2, because we have to make it go through the point 2, -1. So if we go back to our number line. So from 0 to 2, we can say it's decreasing, concave down, shaped like a front. And it levels off at 0 there. So from 0 to 2, decreasing, concave down. So decreasing, concave down. Again, making a nice smooth transition because the first derivative exists there. It's negative. And I leveled it off here because the first derivative is 0 there. So again, don't worry about having the exact y value as long as it's decreasing, concave down. It's got to start above this point in order to be decreasing. Then if we look back from -3 to 0, it's increasing, concave down, shaped like a front. So from -3 to 0, increasing, concave down. So to increase to get to that point, it has to start below it. Something like that. Oops, that's a little off there. Let me try to graph a little better. There we go. Let's go back. So increasing, concave down, shaped like a front. Then let's go back to our number line again. Next time something changes, -6. -6 to -3, increasing, concave up, shaped like a cup. And notice it levels off at 6. So increasing, concave up. So in order to increase to get that point, it starts to start below it. Increasing, concave up, levels off right there. And finally, from -8 to -6, it's increasing, concave down, shaped like a front. So in order to increase to get to this point, again, it has to start below it. So increasing, concave down. Just let me try that one more time. There we go. So increasing, concave down. So that would be a possible graph of f. Again, the points we know for certain are the 2, -1, and these 2 points, because it was linear, and then we found the slope was exactly -2. And the rest of it, the y values don't have to be exactly where I have them, but you do need to have the correct increasing, decreasing intervals and concavity, concave up or concave down. And that concludes the notes on the topic of analyzing the graph of the first derivative.